Welcome back to NE 630, sorry, the nuclear reactor theory class. And we will be continuing the same business like before last time. So last time we discussed the solution of the time-dependent diffusion equation in medii, where we have a disbursement of fissile material, and we call it multiplication medium. So last time we derived the formula for a slab geometry, excuse me, and we showed that the flux can be represented as a summation of eigenvalues multiplied by each other, and it was an, where an is a constant multiplied by e to the power of minus lambda 1 t, which is lambda n, and lambda n is eigenvalue, and I will show you what's the eigenvalue in a minute, multiplied by time, multiplied by cosine bnx. And this was the flux shape in a slab, which is just a cosine shape which has a maximum in the center and zero in the border or at extrapolated distance. So the main goal for last time is to calculate what is the shape of the flux based on a uniformly distributed fission source or fission material, fissile material inside the slab reactor. So let's continue the business, and hopefully if we have time we'll go ahead and also try to calculate the flux in a cylindrical geometry and in a spherical geometry. But we try to make things easier and simple by just looking for a reduced equation that can tell us when the reactor will be critical or subcritical or supercritical, and what are the conditions. So last time also we showed that we can calculate the constant n by just making use of the orthogonality property of eigenfunctions. We multiplied last time both sides by cosine of mx, and then we integrated over the whole period, and then we were able to calculate what is the constant. So now, if you remember, I told you last time that b1, the constant b1, was less than b2, was less than b3, was less than up to bn, and this is because bn is just nothing more than n multiplied by what? A extrapolated over by over a extrapolated, and with the increase of n, bn will increase also. And again, lambda 1 lambda 1 was less than lambda 2, again less than lambda 3, and less than lambda n. So now let's look for what do we mean by lambda. If you remember our equation was given by phi of x and t is equal to summation over n, and this is an e to the power of minus lambda n multiplied by time t multiplied by cosine, and Pn is just nothing more than n by over a extrapolated multiplied by x. So this was the flux last time. So now we stated last time that whenever n will increase, lambda n will do what? Will increase. So what happened for higher values of lambda n? This term will be what? Going to zero. So all those harmonics will die away or die out except the first harmonic. So we can write the flux as a function of x and t based only on the first harmonic, and this will be a1 e to the power of minus lambda 1 t cosine by x over a extrapolated. Now let's look for three cases for lambda 1. So what happened for lambda 1 when lambda 1 is 0, and when lambda 1 is greater than 0, and when lambda 1 is less than 0? What happened with in the case where we have lambda 1 is equal to 0? I have a flux is what? Yeah, but what does it mean? Yeah, it's independent of time. What does it mean in nuclear reactor physics or nuclear engineering? You have a flux independent of time. What does mean steady state in nuclear reaction? A critical reactor. So this is what? Critical reactor. The reactor is critical, there is no change. So now, what if the lambda 1 is positive, is greater than 0? So what will happen if lambda 1 is positive? The flux will die out with what? With time. So what does it mean when you have a flux going down with time? Subcritical. So this is subcritical. And the last case when lambda is negative. So excuse me, if lambda is negative, negative by negative is positive. E to the power of positive quantity is a positive quantity increasing with time. So what does it mean? The flux will be the same flux, but it will have what? Amplitude that grow up with time. What does it mean? So this is supercritical situation. So did you understand now what does it mean lambdas? We will notice by the end of this lecture, maybe, or next lecture, that lambda can be correlated to the effective multiplication factor. It is not the multiplication factor. It can be correlated to the multiplication factor. We will show by the end of this lecture. So now, what was the definition of lambda the last time? Lambda was just what? Was the constant when we solved the differential equation using the what? Separation of variable technique. And we notice that there is two functions. Each one has a variable t, and the other one has a variable what? X. And they are totally independent, but they are equal to what? 0. So each one of those should equal to what? A constant, and the constant should be the same. So this is why we call it lambda. But we notice that lambda depends finally on what? Depends on n. Yes. So this is why we call it lambda n. So lambda n was equal to what? Equal to the velocity, if you return back to your last lecture, multiplied by sigma absorption plus diffusion constant multiplied by b square. We will call this b square g for a reason that will be clear in a minute, nu sigma fission. So this is just the velocity, and this is just nu, the number of neutron emitted per fission. So this bg, I will call it bg for a reason now, and we'll discover now what does mean. So when lambda we call it where n equal to 1, which is the first harmonic, and this is we call it lambda 1, and this will be v sigma absorption plus d, and this is b1. bg is just b1, so bg is b1 minus nu sigma fission. So now when lambda 1 equal to 0, let's see what's going on. So our reactor is now what? Critical. So try to work with me here. You will notice that I need to get BG in one side. So BG, I will get it here. I will take V multiplied by sigma absorption and V multiplied by nu sigma fission. Of course, I can cancel V, by the way, because this is equal to 0. So I can divide by V and nothing will happen. Then I will take this term and this term and move them to the other side. So this will give me what? Nu sigma fission minus what? Sigma absorption over D. And if I take from the upstairs sigma absorption as a constant, so this will give me nu sigma fission divided by sigma absorption. And D will be outside, but I can still put D here to be the denominator of sigma absorption. So minus 1. So what's this? Everybody is following up what I'm doing. I don't think that I did anything extra. It's just math. So now what's nu sigma fission divided by sigma absorption? Nope, this is not eta. This is nu sigma fission divided by sigma absorption in the fuel multiplied by sigma absorption in the fuel divided by sigma absorption. This is sigma absorption total. It's not sigma absorption in the fuel. This is total. Did I, in the diffusion equation, did I specify sigma absorption in fuel or in anything? No, this is the total absorption. So this is the total absorption. So now if I divide by sigma absorption fuel and I multiply by sigma absorption fuel, this is eta. And this is what? F. So eta F. If I multiply by P and I multiply by epsilon, I say I do not have epsilon. I do not have fast fission. I will neglect fast fission. So what this will be? 1. And if I say I am an infinite multiplying system and the resonance escape probability is almost 1. So this is what? 1. Let's assume that it is 1. So what's this? K infinity. Yes, guys? So this is K infinity. So in infinite multiplying system, I will have K infinity equal to what? F multiplied by eta. Now, and what's this? This is just L squared. So this will be K infinity minus 1 divided by L squared. Guys, this factor here, nu is a function of what? A function of energy, but it's a property of what? Material, of fuel. Sigma fuel and sigma absorption is properties what? Material inside the reactor. D and sigma absorption is property of what? Material inside the reactor. So I can call this guy here B square M. So why I'm saying this? So this is called material buckling because it just depends on material. So material buckling, and this is called geometrical buckling for a reason that will be clear in a second. So the geometrical, when you have a critical reactor, your geometrical buckling will be equal to your material buckling. So why we call this one geometrical buckling? This is the reason now we call it material buckling, because it depends only on material. But what about the other one? If you remember the equation that we solved, it was nabla square phi plus b square phi equal to 0. And this is the geometrical buckling. Yes? This is when we solved the problem at the very early beginning, it was just called b square. But we figure out that this b square is bn. Yes? b1, b2, b3, b blah, blah, blah. And we call it b1, we call it b1. When we get b1, we call b1 geometrical buckling. Why? Because if you look at this, what's bg here? Let's say we are talking about two-dimensional geometry in x dimension. So this will be 2 phi by dx square plus b square g phi equal to 0. So b square g will be nothing more than negative 1 over phi d2 phi by dx square. Geometrically, what does it mean, the second derivative of a function? What? Do you know what does it mean, the second derivative of a function? Curvature. Exactly. So when you have the first derivative, this is the slope. When you have the second derivative, this is what? The curvature. So if you have, let's assume that you have the equation of r, let's say this is the radius of curvature, equal to x squared plus y squared. Okay? So when you get, let's say r is constant, and when you try to do dy by dx, then you get d2y by dx square, you will notice that d2y by dx square goes like 1 over r. So the curvature goes like 1 over the radius of curvature. So when you have a line, what's the radius of curvature of the line? Infinity. Yes? So what's the curvature for this line? 0. So the curvature is 0 and the radius of curvature is infinity. Yes? But when you talk about something like this, so this has a radius of curvature r. If you invert the radius of curvature, this will give you the curvature of the circle. Okay, guys? Okay, so what if your radius of curvature infinity? Infinite radius of curvature. So your curvature is what? Is 0. It's like a, I don't know, maybe a point or something like this. Okay, guys? So this is just why we call this the curvature. So this is a property of what? Of the geometry, of the shape of the reactor. So this is why we call it geometrical buckling. So it depends on the geometry of our reactor. So if our reactor is compact like this, and our reactor is large like this, which one will have more curvature? This one will have more curvature, because if you inflate this, you will get a radius of curvature. Inflate it like the universe, very large. So it's like flat. You will look at it as a flat. It's like when you look at the Earth from like just on the surface of the Earth, and you are looking at the Earth, it's flat. Why? Because your dimension with respect to the radius of curvature, which is the radius of the Earth, is nothing. A meter or 2 meters with respect to 6,000 kilometers. But when you are very far away on the airplane, or maybe in something else, your distance from the Earth now is very large, and maybe it's comparable to the radius of curvature. So you will be able to see the curvature of the thing. So again, so this is why we call this geometrical buckling. So whenever your geometrical buckling equal to your material buckling, your reactor is critical. You have a critical mass. So whenever you have a geometrical buckling equal to material buckling, you have a critical mass. So this is usually in nuclear engineering, if you want to say, okay, calculate the geometrical buckling, calculate the material buckling, see if both are equal or not. Now your system is critical. If you do, you will notice that lambda 1 again less than 0, and lambda 1 greater than 0, and lambda 1 is equal to 0. This is critical, and in this case, B square material will be equal to B square geometrical. This one is subcritical, yes? Because lambda 1 is positive and you have a negative sign in the exponential, so it will decay, so this is subcritical. Subcritical means that the material inside your volume is not enough to make you critical. So this means that your material buckling is less than your geometrical buckling. And this one is supercritical, means that your material buckling is greater than your geometrical buckling. So those are the conditions for criticality. Any questions so far? Now, let's look for the case where we do not have criticality. Lambda 1 is not equal to 0. So let's say we will see lambda 1 in general. So lambda 1 in general. So lambda 1 is just V multiplied by sigma absorption minus nu sigma fission plus V d B1 square. Now, I can take, of course, V outside. So lambda 1, I can rewrite this and just concentrate with me. So if I take V sigma absorption outside, so this will be V sigma absorption, and this will be 1 minus nu sigma fission divided by sigma absorption plus d over sigma absorption multiplied by B1 square. Now, do you have any questions so far? Now, I can rewrite this as V sigma absorption multiplied by 1 minus nu sigma fission over sigma absorption plus L square B square 1 equal to lambda 1. Again, I can now take this 1 plus L square L1, can take this as a common factor outside. So this will be V sigma absorption 1 plus B square 1 L square outside. What will be remaining for me? Will be 1 from those two factors. I will have what? 1 minus nu sigma fission over sigma absorption. Divided by what? 1 plus B square L square. Yes, guys? Anything that you do not understand here? Okay. Now, let's look at, this will be lambda 1. Each term individually. V sigma absorption. What's this? This is V, and sigma absorption is what? The mean free path for what? For absorption. Mean free path for absorption. Velocity over distance gives you what? 1 over a time. So this will be equal to 1 over generation time. And this is, I already talked to you about this one. This is the neutron lifetime. Neutron life time. So we define the first term. So let's look for the second term. 1 plus B square L square. I need you to concentrate a lot in this one because it is a little bit different. I have a volume like this, which is my reactor. And then I have sigma absorption phi, which is the total number of absorption inside this volume per centimeter cube per second. And I have divergence J. What's divergence J, by the way? What's divergence J? So it's the outward leakage, yes? Because it is the net inward and outward, yes? So it will be outward minus inward, so it will be the net outward. And this is a volume and it has certain surface here. I will take delta S as the surface here. So what is the leakage rate? Leakage What's the leakage rate? The leakage rate is nothing more than J, the number of neutron per centimeter square per second net in, let's say, in output direction dot ds. And you will integrate over the whole surface. Yes, guys? So this is the net output here. But what's J? What's if you have, do you know the Green theorem? If you have a certain vector, let's say f, and you integrate this vector over an area, this should give you what? This is an area here. This should give you what? The divergence of the same vector integrated over volume, and this is volume here. What does mean this divergence theorem said? It said that the net outflow of the vector f, yes, is equal to the divergence inside this volume of this output of the same value of f. Let's assume that f here is, let's say, electric field. Okay, so electric field represented, let's say, E dot A. So the integration of the electric field over the surface, if you will get the divergence of the electric field is the integrated over the volume, this will give you the charge. So it tells you that the source of the electric field on the surface is coming from the charge inside the volume. This is just, so the same, the source of neutrons in the surface are coming from whatever change inside the volume. So this is just a physics. So we can change this J dot ds to what? Divergence J over what? Over the volume. And what's J? J is negative d grad phi. So this will give me what? Divergence of d grad phi dv. So if d is constant, I can take d outside, and this will give me what? Negative d nabla square phi dv. But from our slab, when we talk about our slab, our flux in the slab is what? As a function of dimension. Our flux as a function of x goes like what? Cosine b1 x. Yes, guys? So if you differentiate this d phi by the x once, this will give you negative b1 sine x. If you differentiate it another one, this will give you what? Negative b square 1 cosine x. Yes, guys? So this means that d2 phi by the x square is nothing more than b square 1 multiplied by the same function phi again. Yes, because this is the same function again. And this is the problem. This is the eigenvalue problem. d2 phi by the x square equal to negative b square 1 phi. This is the problem that I just erased it from here. This is the original problem. Nabla square phi plus b square 1 phi equal to 0. I'm just prove it to you that it is true for a cosine shape function. Yes? So I can remove nabla square from here, and I can put, instead of nabla square, I can put what? I can put what? So minus multiplied by minus, so I can put minus what? B square 1 multiplied by phi. Yes? So this will give me what? This will give me d b square 1, the integration of phi dv. Now, let's try to calculate this quantity. Rate of neutron absorption. How many neutron absorbed per centimeter cube per second, or total in the whole volume, divided by rate of neutron absorption plus rate of neutron leak out. What's this quantity? Let's assume that I have 1,000,000 neutrons inside my volume. I said that I have 700,000 out of the 1,000,000 absorbed inside the volume, and 300,000 will leak. So if you divide 700,000 by 300,000 plus 700,000, which is the 1,000,000 again, this will give you 0.7. So what does mean the 0.7? What does it mean?
Fraction non-leakage?
Yes, the non-leakage probability. So this is what? This is the non-leakage probability. You remember where we studied the non-leakage probability? In the K effective, we said that it's K infinity multiplied by the non-leakage probability, fast and thermal. You remember? So this is the time where we will calculate now the non-leakage probability. So non-leakage probability is equal to rate of neutron absorption divided by absorption plus leakage, equal to, what's the rate of neutron absorption? It's the sigma absorption multiplied by the flux integrated over the whole volume. This is the total number of neutron absorbed in the volume. Yes? So what's I will drop it back again here, sigma absorption phi dv plus, what's the rate of neutron leakage? Here it is, the leakage rate. Yes? So what's the leakage rate? It's d b square what? 1 multiplied by what? Phi d what? Phi dv. So if the sigma absorption is constant, I can take sigma absorption here, and I can take sigma absorption here. So I will end up with what? The integration of phi dV, and the integration of phi dV, and the integration of what? Phi dV. So this will give me what? Sigma absorption divided by what? By sigma absorption plus d b square 1. Come on, guys. Do you agree? Sigma absorption over sigma absorption plus d b1 square. I eliminated d phi. I take sigma absorption from here outside, so I will eliminate this. And I will take sigma absorption from here outside, and I will eliminate this with this with this. I will end up with this. So if I take sigma absorption as a common factor from upstairs, I divide up and down by sigma absorption. So this will give me what? 1 upstairs and 1 downstairs plus d over sigma absorption b1 square. What's this? 1 over 1 plus lambda square, L square multiplied by b1 squared. What's this? The non-leakage probability. This is the probability of non-leakage. Yes? So what's this term? What's this term? Look at over there. So this term is what? 1 over the non-leakage probability. By the way, you will not find this in the Stacy book, so you have to follow me up. Okay, guys? So this is what? The non-leakage probability. Now, we knew that this is 1 over L, and this is 1 over P and L. And what's new sigma? What's new sigma fission over sigma absorption? K what? K infinity. If you multiply, okay, this is nothing more than K infinity. Yes? So this term is K infinity. And 1 over this is what? So this term here is nothing more than K infinity multiplied by P and L. What's this? K effective. The effective multiplication factor. So I can write lambda 1 as equal to what? 1 minus K effective. Yes, guys? Divided by what? L multiplied by what? So if this is the multiplication factor for infinite what? For infinite system. If I multiply it by the non-leakage probability, this will give me the neutron lifetime in a finite system. Yes? This is the sigma absorption multiplied by V is just the mean free path, and this is what? Velocity. But this is if you are in an infinite system. But bunch of those neutrons will escape. So do you expect in an infinite system the neutron will stay longer or shorter compared to a finite system? Longer, because there is no border that will come near to and it will leak. So I have, if I multiply the infinite lifetime for the neutron lifetime by the non-leakage probability, indeed it will tell me that, okay, this is just L prime. So now L1 is nothing more than now 1 minus K effective divided by L prime. So L now is what? Is inverse time. Inverse what? Inverse time. Yes? Lambda, sorry, not L. Lambda is inverse time. Yes, because this is time, and this is constant, 1, and the K effective is what? It's a constant, it's a number. Number, but this is a time. This does not have any units. This does not have any units, but this is what? It has seconds on it. So lambda is what? Second minus 1. And this is very, very true. Why? Because if you look at e to the power of minus lambda t, any exponent should have what? Dimensionless. So if this is time, this should be what? Inverse time. And this is what we prove. So if this is time, this is inverse time. Okay? So did you understand? Yes, Muhammad.
L is the neutral lifetime. So what's L dash?
This is for infinite system. This is for lifetime for infinite system. So this is a neutron lifetime for finite system. Okay, guys? Okay, guys? Now, I can now rewrite it as this equation. I can rewrite it as minus lambda is equal to 1 minus, sorry, is equal to K effective minus 1 divided by what? L prime. So this is, I write it this way because if K is greater than 1, I will get what? I will get a positive number here, okay? And if K is less than 1, I will get a negative number and so on. So, huh?
Is that lambda 1?
Yeah, this is lambda 1. Thank you. So now, when lambda 1 also equal to what? If you play with the very early definition for lambda 1, which is what? V multiplied by sigma absorption minus nu sigma fission plus d b1 square equal to lambda 1. So if you rearrange, you will notice that this is V multiplied by b square geometrical minus e square material, and there is d here. So those are the definition for lambda 1. So now, when lambda 1 is equal to 0, what will happen? Bg equal to what? B square m. Look up here. Lambda 1 is equal to 0. 0 multiplied by L is 0, and K effective is equal to what? And this is the condition for criticality. In order to have your reactor critical, you have to have what? Your K effective equal to what? Equal to 1. And K effective equal to 1, K effective is just nu sigma fission divided by sigma absorption divided by 1 plus L square B1 square. Did you understand? So I think I will stop here because I have to go to start the new topic about the cylindrical reactor, and if I start, you will curse me until next lecture. So it's better to stop here and then make you refresh from the beginning next time about the cylindrical geometry. Do you have any questions? Any comments?
Could you move over a little bit?
Yeah, thank you. You're more than welcome. Here it is. Guys, anything else? Have a wonderful time. See you next week. Next lecture.